The Dance of Photons, Understanding Radiation Heat Transfer. Imagine a campfire on a chilly night. You feel its warmth even from a distance. This invisible energy transfer is radiation. It's the same phenomenon that warms our planet from the sun's rays. We can't see these energy waves, but we can certainly feel their effects. In the world of engineering, understanding radiation heat transfer is crucial. It plays a vital role in designing everything from power plants to spacecraft. These systems operate at extreme temperatures where radiation becomes a dominant mode of heat transfer. Accurate simulations are essential for predicting performance and ensuring safety. That's where ANSYS FLUENT comes in. It's a powerful tool that allows engineers to model and analyze complex heat transfer phenomena, including radiation. With FLUENT, we can simulate how heat radiates from one object to another, even in the vacuum of space. This ability to model the invisible dance of photons is revolutionizing how we design and optimize our technological world. The ANSYS FLUENT's toolbox, a spectrum of radiation models. ANSYS FLUENT offers a range of radiation models, each with its strengths and limitations. Think of them as different lenses through which we can view the complex world of radiation heat transfer. The choice of model depends on the specific problem at hand. Factors like optical thickness, computational cost, and accuracy requirements all come into play. Let's explore some of the key radiation models in FLUENT's arsenal. We'll delve into the intricacies of the surface-to-surface, S2S, Discrete Ordinates, DO, Discrete Transfer Radiation Model, DTRM, P1 Model, and Rosseland Model. Each model offers a unique perspective on how photons travel and interact with their surroundings. By understanding the principles behind each model, engineers can make informed decisions about which one best suits their simulation needs. This selection process is crucial for obtaining accurate and reliable results. Surface-to-surface, S2S, a clear line of sight. The surface-to-surface, S2S model is like having a clear line of sight between objects exchanging radiation. It assumes that the medium between surfaces does not participate in the radiation process. This makes it computationally efficient, especially for enclosures with a large number of surfaces. Imagine a solar oven where sunlight streams in and heats the cooking chamber. The S2S model would be ideal here, as the air inside the oven doesn't significantly absorb or scatter the radiation. However, S2S has limitations. It stumbles when dealing with participating media, like combustion gases or pulverized coal flames. These media absorb, emit, and scatter radiation, making the path of photons less straightforward. In such cases, other models like DO or DTRM are more suitable. Despite its limitations, S2S remains a valuable tool for many engineering applications. Its simplicity and speed make it a popular choice for design optimization and preliminary analysis. It's essential to understand when its assumptions hold true to ensure accurate results. Discrete Ordinates DO, marching orders for photons. The Discrete Ordinates DO model is like a well-organized army of photons marching in specific directions. It divides the radiation field into discrete, angular directions, tracking how photons travel and interact with the medium along these paths. This model shines in situations where the participating medium plays a significant role, such as in combustion chambers or atmospheric radiation. It can handle complex geometries and accurately capture the scattering and absorption of radiation by gases and particles. However, this accuracy comes at a computational cost. The DO model requires solving the radiative transfer equation for each ordinate direction, making it more computationally demanding than S2S. The number of ordinates chosen directly impacts the accuracy and computational time. Despite its computational cost, the DO model remains a powerful tool for simulating radiation in participating media. It's particularly useful in applications where accurately capturing the directional nature of radiation is crucial. Section 5. Discrete Transfer Radiation Model, DTRM, following photons on their journey. The Discrete Transfer Radiation Model, or DTRM, takes a more statistical approach to tracking photons. Imagine releasing a swarm of fireflies into a forest and observing their paths. DTRM follows a similar principle, tracing the path of representative photon bundles as they travel through the medium. This model strikes a balance between accuracy and computational cost. It's less computationally intensive than DO, while still accounting for the participating media effects. DTRM is suitable for a wide range of applications, from furnaces to solar receivers. It's particularly useful when dealing with complex geometries and non-gray media, where the absorption and scattering properties of the medium vary with wavelength. However, DTRM's accuracy depends on the number of photon bundles used and the angular discretization, similar to the DO model. Overall, DTRM provides a robust and versatile approach to modeling radiation heat transfer in participating media. Its ability to handle complex geometries and non-gray effects makes it a valuable tool for many engineering simulations. Section 6P1, Model, a simpler light show for complex problems. The P1 model simplifies the radiation field by approximating it with a series of spherical harmonics. Imagine replacing a complex light show with a single, diffuse light source. While not as accurate as DO or DTRM, the P1 model offers a significant computational advantage. This model is particularly useful in large-scale simulations where computational resources are limited. It's often employed in combustion simulations, where the radiation field is relatively isotropic, meaning it's fairly uniform in all directions. However, the P1 model's simplicity comes with limitations. It struggles in situations with highly anisotropic radiation, such as near surfaces or in optically thin media. In such cases, the more computationally expensive DO or DTRM models might be necessary. Despite its limitations, the P1 model remains a valuable tool for obtaining reasonable engineering approximations in computationally demanding simulations. It allows for a quick assessment of radiation effects and can guide further analysis using more sophisticated models. Section 7, Rosseland Model. When the medium is dense with photons. The Rosseland model is like swimming through a thick fog. It's used when the participating medium is optically thick, meaning radiation can only travel a short distance before being absorbed or scattered. In such cases, the radiation field becomes diffusion-dominated. This model simplifies the radiative transfer equation, assuming that the radiation intensity is primarily determined by the local temperature gradient. This simplification makes it computationally very efficient, especially for large-scale simulations involving optically thick media. However, the Rosseland model's simplicity comes with limitations. It's not suitable for optically thin media or near surfaces, where the diffusion approximation breaks down. In these situations, other models like DO or DTRM are more appropriate. Despite its limitations, the Rosseland model remains a valuable tool for specific applications. It's commonly used in modeling stellar and planetary atmospheres, where the optical thickness is extremely high. Section 8. Choosing your lightsaber. Selecting the right radiation model. Selecting the appropriate radiation model is crucial for obtaining accurate simulation results. It's like choosing the right lightsaber for a Jedi Knight. The wrong choice can lead to inaccurate predictions and misleading conclusions. Optical thickness is a key factor in this decision-making process. For optically thin media, where radiation travels relatively freely, the S2S model might suffice. As the medium becomes optically thicker, models like DO, DTRM or P1 become more suitable. For extremely thick media, the Rosseland model offers a computationally efficient approach. Other factors to consider include the complexity of the geometry, the presence of non-gray media and the desired accuracy level. Each model has its strengths and weaknesses, and the best choice depends on the specific problem at hand. It's essential to carefully consider the assumptions and limitations of each model before making a selection. Consulting the ANSYS FLUENT documentation and seeking expert advice can aid in this process. Section 9. Illuminating the results post-processing radiation data. Once the simulation is complete, it's time to analyze the results. ANSYS FLUENT provides a range of post-processing tools to visualize and interpret radiation data. These tools allow engineers to generate temperature contours, radiation flux plots, and other visualizations to understand how radiation affects the system's behavior. For instance, in a combustion chamber, engineers can visualize the radiative heat flux distribution to identify hotspots and optimize the design. Fluent also allows for the calculation of radiative properties like emissivity and absorptivity, which are crucial for understanding how different materials interact with radiation. By analyzing these properties, engineers can select appropriate materials for specific applications. Effective post-processing of radiation data is essential for extracting meaningful insights from simulations. It allows engineers to validate their models, identify design improvements, and optimize system performance. Section 10. Real-world applications from combustion engines to solar panels. The applications of radiation heat transfer modeling are vast and diverse. From designing efficient combustion engines to optimizing solar panel performance, radiation plays a crucial role in numerous engineering fields. In the automotive industry, engineers use Fluent to simulate the combustion process inside engines. By accurately modeling the radiative heat transfer from the flame to the cylinder walls, they can optimize the engine design for improved fuel efficiency and reduced emissions. In the aerospace industry, radiation modeling is crucial for spacecraft thermal management. Satellites orbiting Earth experience extreme temperature variations as they pass between sunlight and shadow. Fluent helps engineers design thermal control systems that maintain the spacecraft within acceptable temperature limits. In the energy sector, radiation modeling plays a vital role in designing efficient solar thermal power plants. These plants use mirrors to concentrate sunlight onto a receiver, heating a fluid that drives a turbine to generate electricity. Fluent helps optimize the receiver design for maximum heat absorption and minimal losses. These are just a few examples of how radiation heat transfer modeling is used in real-world applications. As technology advances and we strive for greater efficiency and sustainability, the importance of accurate radiation simulations will only continue to grow. Section 11. The future of radiant simulations. Brighter insights ahead. The field of radiation heat transfer modeling is constantly evolving. As computational power increases and new algorithms are developed, we can expect even more accurate and efficient simulation tools in the future. One exciting area of development is the integration of artificial intelligence and machine learning into radiation modeling. AI and ML algorithms can analyze vast amounts of data from experiments and simulations to improve the accuracy and efficiency of radiation models. Another promising area is the development of coupled simulations that combine radiation heat transfer with other physical phenomena, such as fluid flow and chemical reactions. These coupled simulations provide a more complete and realistic representation of complex systems. The future of radiation heat transfer modeling is bright. As simulation tools become more powerful and sophisticated, they will continue to play a vital role in driving innovation and solving complex engineering challenges across a wide range of industries. By harnessing the power of radiation modeling, we can unlock new possibilities for a more sustainable and technologically advanced future.